Okay, so good morning, afternoon, or evening, everyone, and thank you for giving me the opportunity to talk to you today. I will talk about PAHs and dust in star-forming regions and PDRs, and I will focus about differences between what we could do from ground-based infrared observation in the JWST area. And so for the purpose of this talk, I'm going to refer to, I'm going to use the nomenclature PHs, and I'm going to be very general here. I'm going to refer to PHs, their cousins, clusters, nanoparticles, all within that one term, PHs, just for ease of presentation, unless I specify otherwise. And so we all have heard already this week about PAH emission. So we're talking about very broad emission features in the infrared. And I'm sorry, I'm rearranging my screen here. And so here you see an isospectrum from the Orion Bar showing the richness of the different bands that we are talking about. And so the main thing that I want to focus here in the beginning of this talk is that these PHs and particles reside in photodissociation regions. And so PDRs, in short, are regions where far UV photons, and that means with energies between 6 and 13.6 eV, dominate the physics and chemistry. And classically, PDRs have been associated with H2 regions because if you go look at this figure here on the left, you can see your massive stars that will create a region of ionized gas because of their strong and hard radiation field. But at some point, you cross the ionization front where hydrogen goes to neutral, and that's where your PDR basically starts, where you will find the PAHs, carbon plus oxygen. And if you go somewhat deeper into the PDR, you can see that neutral hydrogen convert into molecular hydrogen. And then even further deeper, you see that your carbon plus on the surface layers will eventually convert into CO. And so the main thing what I want you to take home of this image here is that you have actually a very nice layered structure. Just going from the left, you have the ionized gas, then you have a new layer where you have the neutral gas, a new layer where you have molecular hydrogen, and then at some point, another layer where you both have molecular hydrogen and CO. And so these are the regions here in the middle between the ionized gas and the cold molecular cloud where your PHs reside. And so PDRs, yes, they are associated with classical star-forming regions, but they're also associated with illuminated diffuse clouds, surfaces of molecular clouds, protoplanetary disk, globules, reflection nebula, planetary nebula, the interstellar medium, star-forming galaxies, ULEX. And so PDRs are widespread in our universe, and so are PHs. Moreover, PHs are quite abundant. And so because of their big abundance, they are key players in PDRs. And what does that mean? They play an important role in that are ongoing in PDRs. The first one, or the main one, is really that they're the dominant heating source in the neutral ISM. So they set the temperature of those regions. They partake in chemical reactions and they influence the charge balance because these molecules and particles can be charged. And so because you change the charge balance, you change the charge state of the gas, and that of course influence other chemical reactions, and as well as how the gas interacts with magnetic fields. They have very large surface areas, and so they enhance surface chemistry. And also it has been shown that PAHs, if embedded in ices, and they see some UV radiation, they get processed and converted into prebiotic molecules. And so overall, all of these processes are actually important if you want to think about, you know, the large-scale processes of star formation and planet formation, but also how we want to study star formation in the universe. Because if you look at galaxies where there's active star formation going on, you see a strong emission of PAHs. And so they're very easy to detect. Now, what we've seen in the last couple of years is that we know that we know for a long time that we're dealing with the population of particles, and that the main characteristics of these of their emission is set by the charge balance. And so fairly recently, there was a study done into reflection nebula where you look at the spatial distribution of the main PAH features in the mid-infrared. And amazingly, 98% of the entire variation in the PAH fluxes could be explained by only two variables. And one was the amount of PAH emission, which is set by the abundance of PAHs as well as their excitation. In this case, in reflection nebula, we all heard from a previous talk by Yang Xi that if you go to external galaxies, the metallicity also plays a role in that sense. And so, but here locally, it's the amount of PAH emission. And the second parameter, as I already mentioned, it's the charge state. But so the amazing thing here is that a total of 98% of that variance can be explained by only those two parameters. And if you want to learn more about the population that we're dealing with and try to characterize that, that may be a little bit disappointing, because how can you extract information if 98% is set by just those two components? But we already heard that we have more in our sleeves to extract information about population. And so one thing that we have seen before already this week is that there are now various diagnostic diagrams where you can probe by ratios of the main features, the charge, as well as the size of PAHs. And so this particular diagnostic diagram is based on theoretical calculated spectra of PAHs, but you may also be aware of the diagnostic diagrams of Bruce Duane and collaborators, which there is based on models. And so that means that in addition to charge, we can actually now extract information about the dominant PAH size. And so this has been done by a number of people already. We have Mori in 2012, Croisset 2017, and Knight in 2021. And here I just show you one example that if you go once again in a reflection nebula and you look at this ratio, it's 11/2/3 with distance from the star, that you can actually see that it changes. And so that you can then connect through these diagnostic diagrams with PAH size. The reason why we take 11/2/3 is basically because they're believed to be both from neutral PAHs. They're also very long wavelength range in between them. So that means they're sensitive to the excitation temperature of the PAHs. And so instead of diagnostic diagrams, you may also be familiar with our well-known correlations. You know, I mentioned charge is a driving force, and over the last 20, 30 years, we have seen that that results in very nice correlations between PAHs of ionic versus neutral. But recently, with the advance of Spitzer, where we can have both spatial and spectral information, we have seen that If you look at pH emission in irradiated PDRs, and now you can talk about reflection nebula or compact H2 regions or H2 regions or the diffuse ESM, you see that, for example, here we have two different components that we extract from the emission spectrum, that the reflection nebula have a different correlation compared to the H2 region. And so that's something that came up thanks to Spitzer, as far as I'm aware, that are well-known correlations that we've seen and that we've used extensively to learn something about these properties actually depend on the environment that you're looking at. The same happens if you look at the reflection nebula and you compare the area where you have very strong emission of PAHs to the surrounding ISM. And depending on which features that you take, normalize on 11.2 to get rid of the strength of the PAH emission, you can see that here as well, you find different type of correlations depending on whether you are in an irradiated PDR or whether you are in the surrounding ISM. And so that tells us that what we've been doing so far has much more promise for us to extract more about the population. But at this point, we cannot, or we don't know what the driver is between these differences. In addition, we found that if you, for example, look at a star-forming region, as for example, the Orion Bar, this is the nice stratified structure that I talked to you about before, the ionized gas, the PDR, and the molecular cloud. Here you can also see that between the some power ratios that you see differences in correlation depending on whether you look at the phase on PDR or an edge on PDR. And moreover, our Spitzer spectral maps have shown that if you look at the emission of pure ionic bands as they are known, and you divide them different components, that their spatial morphology is quite distinct. And so that means that we can probe something in these spectral maps that goes beyond charge and size of PAHs. And that tells us that these are just a few examples, and it tells us basically that the population that we are considering are changing under the influence of the radiation field and the local physical conditions. And it's not just the population itself of these large molecules. I already mentioned that if the radiation field is hard, that you destroy the smallest one, but also if the radiation field is very strong, what you can have is for the larger molecules that are able to survive, you strip them from the hydrogen atoms, and then basically they start to curl up and form a cage, and eventually they're going to form the the most stable cage, which is fullerenes. On the other side, much further away from the radiation field, you can see that you have more complex structures like clusters and nanoparticles. And once they get exposed to, although weaker radiation field, the weakest bonds there can also be destroyed, and then you can form these smaller, large molecules. And so we see in the ISM, we have plenty of different observational evidence that we do see this evolution, and not just within the large molecules themselves, but going from kind of nanoparticles to large molecules and also to fullerenes. Now, this is, of course, not only true in the ISM. I only showed you a few examples of the ISM, but also we need to be aware that if you go from an interstellar versus a circumstellar environment, the properties change quite differently. And so here I show you one of the strongest pH bands for three Herbig AB stars. They have all the same spectral type, but you can clearly see that the profiles are shifted and have a different shape. If you go from a circumstellar environment, so the protoplanetary disk, to an environment where the surrounding molecular cloud is dominating the emission. The same holds if you go to older stars, post-JWST stars, protoplanetary nebula, and planetary nebula. You see features that are not seen or not strongly seen in the ISM. And so this is also shown if you go to circumstellar environments. All of the colored profiles that you see in this plot are all seen in circumstellar environments, while the interstellar environments only show the blue profiles. That is not, this is just an example. This is not to say that there are no variations between each of these colors. In fact, you have a smooth transition between the different colors, but the ISM is basically very well represented by the black profiles. And so what do we need to know, or what is our ideal instrument if you want to kind of push this boundary and kind of find the origin of all these differences that we have discovered in the last set of years? And so in an ideal world where there are no restrictions whatsoever and I can dream big, what I really would like to have is I would like to have an instrument that covers the full wavelength range so that we can observe all the PAH emission. We would like to have a medium spectral resolution because we want to see all the weaker bands. We want to see the substructure in the profile. So here is a comparison between a Spitzer spectrum at 60 to 130 resolution and an ISO at 1600, and you can clearly see that there is lots of substructure present in these profiles that are hidden when we go to lower spectral resolution. And of course, if you want to study these big profile variations in the 8 micron region, they tend to be large. But if you go to 3.3, 6.2, and 11.2, they're a lot smaller, and you need a sufficient spectral resolution in order to discern those. In addition, and I also would like to have high spatial resolution, because if you want to study the evolution, including the formation and destruction, you want to have such spatial resolution that you can probe changes on a physical scale that corresponds to the physical scale of these processes. And so that means you want to be able to probe this stratification in a PDR. You also want to be able to probe here. I have an example of a evolved star, and you can see that these bands changes on very, very small spatial scales. And so depending on what type of environment you're looking at, what high means for spatial resolution may vary, but we need a large range in that sense as well. We would like to have a large field of view because instead of looking at a tiny part of an extended source, we would like to get the entire picture and so kind of study the large scale PAH evolution. And also we would like to have a large dynamical range because sometimes we need to study weak targets or weak features, but very often we also have plenty of information in very bright targets. And the very bright targets in this case are, for example, Milky Way targets, planetary nebula, protoplanetary nebula, etc., which can be extremely bright and also extremely small and large, you know. And so in the ideal world, the instrument that we require for this type of studies has those requirements all at the same time, because then if we have that available, we can both localize the spatial location of the different emission components, their substructure, the weaker components, etc. And we can understand the main physical, chemical, dynamical processes that are responsible for how these molecules change. And so if you want to understand in general the key, the evolution of matter, of PAHs and dust, and how one evolves into the other, you need to have both spatial and spectral information. Now, of course, as we heard before in many of the talks earlier this week, infrared observations for their interpretation, it's very useful if you actually also have information from other wavelengths. And so in this particular case, for the interpretation, it really helps if you have the physical characteristics of the PDR. I'm talking about density, temperature, radiation field. And so molecular hydrogen is a good tracer for that, which is accessible in the infrared. But we also have very important tracers by the far infrared cooling lines and the far infrared dust continuum. And so those are provided, for example, by SOFIA. We also need to put it in a broader environment. The PDR is kind of located between the ionized gas and the cold molecular cloud. And so we need to put that in perspective. And as I already mentioned a little bit, you would like to know how these molecules, how you go from one type of structure, for example, from nanoparticles into like large molecules, into, for example, fullerenes, small hydrocarbons. These species absorb radiation, of course, and we need to find what the absorption characteristics are for these species. And so that means we need to look at the extinction curve as well as the diffuse interstellar bands. And so we've heard already that JWST will, revolutionize astronomy in many different ways. And it is certainly the case also when you talk about PAHs and dust. And because it will give you the full wavelength coverage, it has instruments that provide you medium spectral resolution. And depending on how you define high, it also has a high spatial resolution, in particular if you compare it with prior Spitzer and ISO observations. However, if you want to have those components simultaneously, you need to do IFU observations, and the field of view of these IFUs are very small. And while JWST is very sensitive and very good to study weak targets, it is limited in dynamic range on the high end. And so very bright targets in our Milky Way are basically out of reach with JWST. Nevertheless, this unique set of capabilities will change this field dramatically. And I'm just going to talk very briefly around one particular program that relates or will explore that. And so this is the early release science program, PDRs for All. And so I'm sorry?
Maybe it's almost the end of your talk, but.
Oh, I'm sorry.
Sorry,
I didn't see you.
Sorry, I didn't.
Okay. I will wrap up as.
Yeah, please.
And so here we can take advantage of JWST capabilities to kind of probe the stratification that I talked to you before in the PDR, going from the ionized gas to the PDR, the dissociation front, and the PDR molecular zone. And so I don't have to tell you that, of course, if you go to these different type of regions, these what you will expect as spectral signatures will be completely different. And so the spatial resolution is so high that if you look at the Orion bar, we can actually probe or resolve these different layers in the PDR. And so we're very hopeful that we can learn a lot about the physical and chemical processes that drive these changes in this population. Now, since I have to wrap up, I would like to contrast the ground-based infrared instruments to JWST. The disadvantage is that you have only partial wavelength coverage, and that may hamper some of the studies that you can do with ground-based infrared observations. However, you have much higher spatial resolution, and you also have a larger field of view and a higher saturation limit. And so that you can use in very different ways. Here you see once again the Orion bar that we will observe with JWST. And here in the inset, you see an ALMA image. And you can see that despite what I've told you, that we have a very nice stratification, you see a whole lot of substructure. And we recently also observed near-infrared KEC data in molecular hydrogen, and we see that, we see a very high substructure, filaments, etc., on a scale which is much smaller than the spatial scale for JWST. And so that means that even for the Orion bar, JWST spatial resolution may not be sufficient to really go into the finest details. I won't mention much about pH evolution in protoplanetary disk because you had already various talks about protoplanetary disk, but do want to mention that you can, both for the disk and in evolved stars, you have different types of molecular emission characteristics. And so now you can actually probe, especially with ground-based observations where these evolved stars are too bright, you can actually probe how the pH and dust forms and processed. And with this, let me thank you for your attention.
Thank you very much. I'm very sorry I forgot to tell you the time, but
yeah, I forgot to watch my clock too. I'm sorry.
Well, there is one question on Slack. It's from Tomek. It's is it possible to observe pH emission from environments poor in UV photons? The cases where pHs are excited by UV from shocks rather than stellar radiation.
Okay, first of all, you don't need UV photons to excite pHs. You can also excite them with visible photons. But UV photons have a higher absorption cross-section, and they, of course, they have more energy. So that means if you have UV photons around, they will dominate the excitation and the emission. Whether you can excite pHs with shocks, I am not aware of, as far as I know. This is typically, if you see shock regions, you actually do not see much pH emission. I remember in the ISO days where they used the existence of pHs to make the distinction between shocks in star-forming regions and UV radiation exciting, for example, the molecular hydrogen.